name is Yamini Pandapagada, and I will be explaining how selection violates the Hardy-Weinberg equilibrium. For this video, I'll be studying the population of rabbits and looking at these three phenotypes and genotypes. Here are the number of individuals per genotype. Our population began in Hardy-Weinberg equilibrium. All of the assumptions were met, meaning there were no mutations, migrations, everyone had equal fitness, and there was random mating and large population size. A chi-square test was also done. Before I show the results of the chi-square test, I'm going to show the genotype and allele frequencies before selection. To calculate genotypic frequencies, you need to divide the number of individuals per genotype by the total population. So for frequency of big A, you would take 150 divided by 700, which would equal 0.214. Similarly, you would do that for the rest of the other genotypes as well. To calculate allele frequencies, you can calculate the total number of A alleles and divide by the total number of alleles in the population. So the frequency of A allele, big A allele, you can do 2 times 150 plus 350 and divide by 700 times 2 because each individual is diploid. To get the frequency of little A allele, you can subtract frequency of big A allele from 1 because the alleles must equal to 1. Here's the chi-square test I was talking about before. So since the chi-square value is below the critical value, we fail to reject the null hypothesis and conclude that our population has Hardy-Weinberg proportions for ear size locus. Now let's see how selection alters the Hardy-Weinberg equilibrium. So in this table of initial genotypic frequencies, the relative fitnesses, and unadjusted survivors, this row equals 0.74, which is the average fitness. This row does not equal 1, so we need to correct the genotypic frequencies, which we can do by dividing unadjusted survivors by average fitness to get these genotypic frequencies after selection. Here is the genotypic array, and we can use these frequencies to find our allele frequencies after selection by following this formula. To find the frequency of big A, you can just add frequency of big A plus 1/2 frequency of big A little a to get your answer. And since the allele frequency should equal 1, you can just subtract the frequency of big A from 1. So immediately what you can notice is that there are more rabbits with big A genotypes and slightly more rabbits with big A genotypes, and there end up being less rabbits with little a genotypes. This shows that there is more selection towards the big A genotypes. If you paid attention to the relative fitnesses in the table, they were leaning towards one direction, specifically towards the big A genotype. This type of selection that occurred was directional selection. This means nature is causing the population to evolve towards one end of the spectrum. In this case, it is leaning towards the big ear trait. This type of selection is occurring because big ears work as an advantage for rabbits. Rabbits have big ears to help detect predators and prevent from getting eaten. If the directional selection is applied to this population over time, the traits that are selected for will permanently increase, while the traits that are selected against will be lost.